for the introduction. And please, everyone, feel free to stop me and ask questions throughout the talk. That'll be great. So today I'm going to talk about language model alignment. And fortunately for me, language models don't need much introduction these days. But for our purposes, a language model is just a neural network trained to produce a distribution over text data, where we're going to denote this distribution by pi theta. Theta is the parameters of our model. What we can do with it, we can give it a prompt X. This is a sequence of tokens, and it gives us a distribution over possible responses Y, also a sequence of tokens. Now, to ensure that these responses are helpful and safe, we need to align our language model after we just trained it over data from the internet. And this is done through some fine-tuning process. One straightforward way to do so is supervised fine-tuning. You collect a set of labeled examples, because these are pairs of prompts and high-quality desired responses, and you just minimize the standard next token prediction loss, the cross-entropy loss over these responses. Now, the simplicity of this approach is very appealing. However, it does come with its limitations. Specifically, it can be quite hard to formalize human preferences using supervised fine-tuning. Let's say we want to reduce the toxicity or the bias of our model. Well, it's not entirely clear how we can do that using supervised fine-tuning. So this led to a wide adoption of methods that use preference data. So here now we have a prompt, and for each prompt, usually a pair of candidate responses. You can sample them from your current language model or get them from anywhere else. What you need human labelers to do is to tell you which one of the responses they prefer. Okay, here they prefer Y plus over Y minus. And the underlying assumption behind these methods, many of them, is that there exists some unknown ground truth reward function RG, which captures at least some aspects of human preferences. And the fact that we see that Y plus is preferred to Y minus, this formally translates to Y plus has a higher ground truth reward than Y minus. We can now formalize the goal of alignment. What we want to do here is we want to maximize this ground truth reward. We want our language model to produce responses that have a higher reward. Now, the main challenge is that we can't directly access this reward. Okay, we can only access it through preference data. So how can we maximize it? In the context of language models, there are two dominant approaches today. And the first is based on reinforcement learning. And the second is a more direct approach of learning based on preference data. And we're going to cover both of them. And as we're going to see, their limited understanding can lead to undesirable outcomes. So the first part of the talk, this is also going to be the main part of the talk. We're going to spend most of the time here. It's on the reinforcement learning approach. It's based on the following three papers. The first was done at Apple during an internship, and the second two at Princeton during my postdoc. And in the second part, it's going to be more brief. We're going to also discuss the direct preference learning methods. So aligning language models using reinforcement learning is also called RLHF, reinforcement learning from human feedback. And it's a two-step process. The first step, we don't have the ground truth reward. So let's learn a proxy reward model. This is a neural network that we train over the preference data to give a high reward to the preferred responses compared to the dispreferred ones. Usually it's through some binary classification type of loss. Once we have our reward model, what we can do is we can maximize this reward. We can align our language model by maximizing the expected reward using policy gradient methods over some set of prompts that we collect. What this amounts to is we want to maximize this objective with respect to our language model, with respect to the parameters of theta. In the context of alignment, the language model is often called also a policy. And so I'm going to use this term interchangeably. Okay, policy, this is simply another term for the language model in these settings. And this objective, you have here an average over your training set of prompts in two terms. The first is we want to maximize the proxy reward, where if our reward model is any good, this should intuitively also increase the ground truth reward that we care about. The second term is a KL regularization with respect to our initial policy. Okay, the idea here is that we want to restrict how much we deviate from where we start from so that we don't lose too much of the capabilities that the model acquired during previous stages of training. Okay, so these two steps is RLHF in a nutshell, and its success heavily depends on the quality of the reward model, right? In the end, the reward model provides the signals for learning. But it's not clear how we should evaluate this quality. Currently, reward models are primarily evaluated through accuracy in how they rank pairs of responses. Formally, for a given prompt X, and some distribution over pairs of responses y and y prime, then our reward model gets a 1 if it ranks correctly these pairs of responses, which just means if it agrees with the ground truth reward in terms of which one is better. And then accuracy is just average this, take an expectation over your chosen distribution of responses. In practice, this is just a data set. And indeed, existing benchmarks, the most popular is called reward bench. They measure exactly this. They collect a set of prompts and pairs of responses, and then they give you this list of which reward model is more accurate over their benchmark. Now, it's natural to look at accuracy because it intuitively quantifies how much, if we maximize our proxy reward model, are we likely to also increase the ground truth reward. If the reward model is very accurate, then responses that it considers to be good are likely also good under the ground truth reward. So it is natural that people measure the quality of a reward model through accuracy and try to perhaps select which reward model to use through these type of benchmarks. But is it true that more accurate reward models are necessarily better teachers for RLHF? And we're going to see that no, this is not the case actually. And to show that, we're going to take an optimization perspective on the problem, which means we're going to consider when does the reward model allow for efficient optimization using these policy gradient methods. Okay, when we run policy gradient, will the reward increase at a satisfactory rate? And we'll look both on the reward that we train on, the proxy reward, but also the ground truth reward that we really care about. And for this part of the talk, we're going to see three main things. So the first is that regardless of how accurate the reward model is, even if it is perfectly accurate, it can still lead to a very flat objective landscape that leads to slow optimization. This is going to be a theoretical result, and based on it, we're going to be able to prove that more accurate reward models are indeed not necessarily better teachers. They can lead to slower optimization. And this is something that you also see in practice. And lastly, we're also going to discuss how this sheds light on limitations of existing reward model benchmarks. So this is the plan going forward for the next part. Are there any questions, perhaps, before we dive in? Okay, great. So please feel free to stop me at any time if there are any questions. The quantity that is going to be important here is reward variance. It's a simple quantity, pretty much what it sounds like. This is the variance of our proxy reward with respect to a policy and a prompt. The randomness here is from responses sampled from the policy, okay? And you're taking the variance of the reward. In other words, this is its exact definition. This is simply the definition of variance. There is nothing hiding here, just to show that it's straightforwardly the variance of this reward. From the perspective of the reward model, which is what we're going to take, intuitively what this measures is how well does the reward model separate the rewards that it gives to responses that are probable under our current policy. If it gives roughly the same reward to all responses that our policy produces, then the variance will be low. But if it does separate them well enough, then it will not. And note that this is in contrast to accuracy, which actually does not depend on the degree of separation. Okay, it only depends on how the reward model ranks pairs of responses. Okay, so effectively, accuracy and reward variance, they measure independent properties of the reward model. Okay? Now, what we show is that reward variance is intimately connected to optimization. Okay, specifically, if it's low, it will take you a long time to increase the reward. Formally, the time that it takes you to increase the expected reward by any additive constant that you choose, and this is going to be true both for the reward that you train with, the proxy reward, and also the ground truth reward, then the time that it takes them to increase grows inversely with the initial reward variance. Okay, this is just an average over our training set of prompts and the variance with respect to the initial policy of the reward. And you have this inverse relation with SAM power, which is not super critical. The main point is as the reward variance is lower initially, it will take you a longer time to increase the expected reward.
Sorry, could you explain how you get RRM?
Yes, so the reward model, usually how you train it, this is a neural network that you train based on your preference data.
Okay.
And this is done usually through some binary classification law. So you train to give a high reward to the preferred response compared to the dispreferred one. And now in this case, now it's fixed. We have a reward model and we're training our policy pi theta. This is the initial policy. We're training pi theta and we're talking about what happens to pi theta, how much it increases. This result is both for the proxy reward, but also for the ground truth reward. Okay, it increases at a rate that is lower bounded by this. Thank you for the question. All right, so why this happens, this is due to the objective landscape that these policy gradient methods induce for language models. Specifically,
We had a question about the power of 1/3.
oh,
Okay.
how do you get? So
So then,
actually, I'm not sure this is fundamental. I think you can improve this to square root. In a simplified setting, actually the bound that you get is -1/2. And I think this is the correct rate. And due to the simplified setting is when you have a single token output. When you have an autoregressive generation, due to just arguments in the proof, you get this power. But I don't believe that it's actually fundamental. Yeah, I believe that maybe you can improve the proof and get here a power of -1/2. And then you can also get a lower bound, at least in simplified settings, with the same power. And where it comes from is basically, we show that the gradient of this expected reward objective vanishes each time that the reward variance is low. And then to get the lower bound, you also need to show that the gradient will not increase rapidly in Noam during training. And this is true for language models, but also more generally for any reinforcement learning setting where you have softmax policies. Okay, this is policies that produce a distribution over actions or outputs using the softmax. So it's a combination of this objective and these type of policies that leads to the connection between reward variance and optimization. And the bottom line is that for allowing efficient optimization, our reward model needs to induce sufficient reward variance. Okay, otherwise we'll have a flat objective that will take us a long time to optimize. Okay, and as you might have noticed, accuracy does not appear in this slide at all. Okay, this doesn't depend on how accurate the reward model is. And indeed, we can use it to prove that more accurate reward models are not necessarily better teachers. For any initial policy that you give me, there exists a perfectly accurate reward model. And on the other hand, you can have a relatively inaccurate one. So it gets almost all pairs incorrectly, but it still needs to get some to work. And for them, you can show that the expected ground truth reward will increase arbitrarily slower if we use the perfectly accurate reward model, as opposed to the relatively inaccurate one. Okay? And I'm giving this extreme case, but actually the result is more general for almost any two accuracy values that you give me. I can give you two reward models of these accuracies. One of them will work well, but the other will lead to low reward variance and slow optimization. And to get a better sense of where this result comes from, I believe it's best to look at an illustration. Here, what I'm showing is the expected reward surface of the ground truth reward. This is what we want to increase. Okay, you can think of the directions here as directions in parameter space. We start here in the gray dot. This is our initial policy. To maximize the ground truth reward, we need to go to the top left. Yeah, if there are any questions via Zoom, please feel free to unmute and just ask. Will I hear it? Is it? Yeah, so just unmute and ask. Feel free to do that. Is there any question now?
Yes. Can you hear me okay?
Yes.
Hi, could you go back to the previous slide?
Yes, of course.
Thank you. So I just want to make sure I understand kind of the order of quantifiers. So you were saying, so should I assume that first there are preferences somehow given by humans that's kind of in the setting of the problem? Then you're telling that for any initial policy, there is a perfect accurate reward which comes from the original preferences which are in the setting. Is that correct? Because basically, usually in reinforcement learning, you just have an environment which includes kind of the reward, and that's just given to you, and then your goal is to optimize this reward.
Right. It's a good question. So the preferences are dictated by the ground truth reward. Okay, so we have this ground truth reward, which is what you really care about. Now here you have another layer, which is as opposed to the standard reinforcement learning settings that you mentioned, where what you're optimizing is actually another proxy reward, which is not exactly the ground truth reward. So these perfectly accurate and relatively inaccurate reward models are the ones that you train with. And the ground truth reward is what you actually care about. Okay, but
Right.
At this point, it doesn't relate directly to the preferences. This is what just the ground truth reward dictates them, but it doesn't relate to this result.
So is the point that this perfect reward depends on the initial policy? That's kind of surprising.
So actually, it doesn't have to depend. You can have the same perfectly accurate reward model for all policies. I think though that's maybe like this is a less interesting case because this is just maybe a poor reward model overall. But it can be interesting if you have a perfectly accurate reward model, which works well for other policies, but not for your policy as well. So you can also change the quantifiers here. The perfectly accurate reward model can be set in advance. This is also true.
Thank you so much.
Great, no problem. So thank you for the question. And yeah, so maybe to give a better sense of where this result comes from. So as I said here, this is the reward surface of the ground truth reward. And for a reward model, accuracy and reward variance measure effectively independent properties, as I said. So for accuracy, it roughly translates to how much the reward model agrees with the ground truth reward in terms of which directions are good. If it is very accurate, it will also tell us, okay, let's go to the top left to maximize the reward. But if it is inaccurate, then it may consider other directions that are actually bad under the ground truth reward as good. This is what leads to reward hacking. Okay, you may increase your proxy reward, but actually decrease the ground truth reward. So accuracy is a beneficial property. We definitely want our reward model to be accurate. But even if it is perfectly accurate and it induces low reward variance, then you'll have a flat objective landscape that will take you a long time to optimize. So this is essentially what our lower bound shows. And then the previous result, the perfectly accurate reward model can lead to a very flat landscape for our policy. While you can have another less accurate reward model, as long as it identifies at least some good directions, okay, and it leads to a high reward variance, you can optimize it faster and increase faster your ground truth reward. Yes.
Is there a way to like tune the hyperparameters or the scheduling so that you increase the speed of the low reward variance?
Yeah, it's a good question. So we did try to do some kind of adaptive normalization schemes. There is a problem that there is a trade-off between how good you're estimating the variance online. So you need to sample multiple responses, which is expensive, and how good this normalization is. So currently we didn't find a good enough trade-off where it's effective to do so. So instead, what we're looking here is, okay, how you can maybe select the reward model in advance so that it induces a better landscape. But this is a very good question of whether you can try to somehow normalize your objective on the fly to mitigate and escape these flat areas.
How do you define the perfectly accurate model?
In our construction specifically, so one example for one is, let's say you take your policy and let's say its probability mass is concentrated on some amount of outputs, or maybe it's even diverse, but your reward model doesn't really distinguish between these responses. It gives them all roughly the same reward. It doesn't matter if this reward is low or mediocre, as long as it's roughly the same reward, you have a low reward variance. So let's say it gives almost all responses a reward around 0.5, but like almost the same reward. The interesting part here is that for your policy, it can, if it doesn't distinguish responses that it produces, but distinguishes other things, then it may be poor for your policy, but also it's not that this reward model is poor in general, maybe just for your policy it's poor. And this is actually the next point that I wanted to make. Okay, first let's see some experiments. Just in practice, you also can widely observe this. This is just a small subset of the experiments that we ran. A standard setting, ultra feedback, preference learning data set, and here it's a 3 billion parameter language model. We're going to look at the increase in ground truth reward as a function of the epochs of policy grading. And we're going to compare just two reward models for simplicity, one which is moderately accurate, 70% accuracy, and another which is actually perfectly accurate, but induces a substantially lower reward variance. And what happens is the red reward model, despite being perfectly accurate, leads to a significantly slower optimization. And so it leads to a slower ground truth reward increase, even though it is perfectly accurate. And more broadly, in other results in our paper and also a couple of other works, you can see that in general, accuracy and how good the reward model is are not that correlated, at least not strongly. Okay, so accuracy is beneficial, but it's not enough to tell you whether the reward model will be good. And the second observation that I'd like to make, which I already alluded to, is that the same reward model can work well for one language model, induce a high reward variance for it, but work poorly for another, induce low reward variance, because reward variance also depends on the language model, the policy. And formally, you can formalize by saying that, okay, you can have two reward models, blue and purple one, and two initial policy families, also a blue and purple one. And the blue reward model will work better for blue policies. The purple one will work better for purple policies. And the reason is just that the blue reward model will induce low reward variance for purple policies and vice versa. This is rather straightforward from what I already showed you, but the interesting point here that I believe is what makes a good reward model when we talk about it or analyze it, this has to depend on the language model that we have. Okay, there may not be this universal sense in which this reward model is better than that one. Okay, and this is also something that you observe in practice widely. Here, I'm showing results from a similar setting as before, but now we have 3 different language models. Each group in this bar plot is a different language model. And we just train them using 4 publicly available reward models. Okay, each color is a different reward model. And for each language model, a different reward model works better. Okay, so existing benchmarks, which measure how good a reward model is over a fixed set of prompts and responses, they're fundamentally limited in what they can tell us about how good this reward model is for our language model. Okay, they are useful, they do tell us something, but in the end, if they are not with respect to your current language model, they may be misleading, right? Yes.
Could you change sampling hyperparameters, whatever language model you're using, to make your model better for that model?
Yeah, so that's also true. You can try to adapt your policy, but at least it's not clear to me. I don't have a good method to do that actually improves this problem. But for example, if you try to just tweak the temperature, then it's not good enough because, for example, if you increase the temperature and lead to more varied outputs, because of the huge output space, this just gives you a more uniform direction, and this more uniform direction, for example, maybe the gradient will not be 0 now, but it's just like a uniform noisy gradient, and because the output space is huge, it doesn't work. Actually, in theory, you can prove that. For example, if you tweak, I think, the temperature or at least entropy regularization, it gives you efficient convergence, but it's efficient in the number of outputs that you have. So for toy settings with a few outputs, then yeah, this is not a problem. You just do regularize your model to be more kind of random. But in language models, this doesn't work. Like both in theory, the bound is not good, and also in practice, you try this and it doesn't work. Yeah, it's a good question. Okay, so to wrap up what we saw until now, we talked about what makes a good reward model for RLHF. And we saw from an optimization perspective that beyond being accurate, which is something that we certainly want, we also need the reward model to induce sufficient reward variance for having efficient optimization. Then we talked about how this shows that more accurate reward models are not necessarily better teachers, in contrast to conventional wisdom, and also how this sheds light on limitations of existing reward model benchmarks. And overall, these results, they highlight that when we design training and evaluation protocols for reward models, we need to take into account properties beyond accuracy. So reward variance is another important property. There may be others as well, though. All right, so I want to spend a few more minutes about reward variance because I believe that is a very important quantity. Specifically, we talked about how it can shed light on what makes a good reward model, but it also depends on the prompt, on the data, and the language model. And so it can also shed light on other aspects of the RLHF pipeline. For example, it can help us explain why doing an initial supervised fine-tuning phase, which is something often people do before running policy gradient, is beneficial in practice. What we see is that when you run supervised fine-tuning, then it substantially reduces the number of prompts that suffer from low reward variance, okay, that suffer from a flat objective landscape. Through our theoretical framework, we can understand this as supervised fine-tuning can help find a less flat initialization for policy gradient, for RLHF. Okay, and this theoretical insight also has a practical application because supervised fine-tuning, it's not a silver bullet. Okay, it requires labeled data, which can be sometimes expensive to obtain. But if at least partially why supervised fine-tuning is helpful is because it helps us find less flat initialization. You just need to nudge your model to a better initialization. Maybe we don't need that many examples. Maybe we just need a small amount just to give us a better head start, and from there, policy gradient will work a lot better. And this is indeed what we find in practice. Okay, in some settings, you can use as few as 1% of the examples that Parawork used for supervised fine-tuning, and you still get roughly the same performance after you do RLHF. This is also something that's been observed in the recent Llama 4 model release, where they mentioned that in the end, out of all the data that collected for supervised fine-tuning, they used only 5% because because they found that within a given compute budget, this is all they needed. This led to the maximum RLHF performance. Okay, so maybe you don't need that much SFT data. And I think there are other results that also show this as well. I think also from Nicolas' group that perhaps supervised fine-tuning, you just need a small amount to get RLHF to work a lot better.
Quick question.
Yes.
So this is great. Yeah, we also saw something like that in some paper we wrote a couple summers ago. But for us, it was about exploration rather than reward variance. Do you think there is a connection there? There's two kind of different explanations.
Yeah, so they're connected. First off, in the sense that exploration, you can roughly say this as currently you're not seeing any response which has a significantly different reward. So this is actually connected, you have a low reward variance. I think the interesting part here beyond that is what we show is that even if you didn't have a problem with exploration, you see all possible responses. In this ideal world, you actually go over all possible responses, compute the reward, compute the exact expected reward gradient, then still you actually have a flat landscape. So this is related, but it shows something a bit beyond that over the landscape that even if you didn't have an exploration problem, there's still a problem due to the objective that you're optimizing.
Thank
Okay,
you.
so I hope, great. Yes, I hope that was clear. And yeah, so this is one practical application, but there are also others for the connection between reward variance and optimization. You can use it, for example, for designing data selection algorithms. Okay, you can try to choose which prompts to train on, where the intuitive idea, something that several follow papers have done, is you can select prompts which enjoy a high reward variance because over them, optimization will be more effective. And then you can try to do these curriculum learning type of algorithms. And you can also try to design policy grading methods, okay, new update rules or reward transformations to try and increase the reward variance and make optimization more effective. And this is also something that several works have done. And this goes to show that, at least in my view, reward variance is a very important quantity. Okay, it's key for the success of RLHF and more broadly for policy grading methods in these settings where you have softmax policies. Okay, at minimum, it can help us identify optimization issues. Okay, which prompts are we not likely to make progress on because they have low reward variance? But beyond that, also for developing new algorithms, as we saw, data selection, policy gradient methods, and perhaps in the future, maybe even reward model training algorithms to induce a better reward variance. Yeah. And now one last remark that I'd like to make on RLHF before moving on. We talked about how properties of the reward model affect RLHF. Now, these properties, they depend on the type of the reward model. For example, it's parameterization, how we produce a reward based on our neural network. And despite the fact that there are several different reward model types, and sometimes they're quite similar, sometimes not, we don't really know the relative advantages or disadvantages. Okay, when should we use which type of reward model? And this is something that we just began to address in a recent paper where we considered how different reward model types tend to generalize differently, especially in absolute distribution in terms of accuracy. Essentially, we show that even seemingly minor design choices can have an outsized effect on how they generalize out of distribution. And the details of this work are more story for another day. But what I do want to say is that there's still much more work to be done here. Okay, we don't understand nearly well enough how the reward model type and its parameterization affects the properties that we get from the reward model, okay, the implicit bias of the reward model type, in other words, and then how these reward model properties translate to what we get after we do our RLHF, our language model. Okay, so this wraps up the main part of the talk. And are there any questions before we move on to discuss direct preference learning?
Maybe a silly one. Is there any connection between the second order derivative, the Hessian of the objective, and the variance of the reward?
Yes, so you can show that also the Hessian vanishes with the brand, and I believe also the higher order derivatives. Yes, so this is kind of the proof. So the gradient vanishes, and then also the gradient can increase fast enough because also the higher order derivatives, they vanish as well. Then you're stuck. Great. So this part will be based on another paper done at Princeton. And these objectives, the main motivation behind them is that RLHF can be computationally expensive. Okay, it can work well, but you need to first train a reward model, which is usually also based on a large language model. And then these policy grading methods, they are notorious for often being unstable. Sometimes you need to tweak their hyperparameters quite a lot to get them to work well. And this led to a question of, okay, do we really need this two-step approach? Can't we just train our language model directly over the preference data? And this is something that several recent methods have proposed. DPO is the most popular one of them. It was proposed a couple of years ago, but now there are multiple other variants. The idea here is very clean. Okay, you take your preference data and just plug it into some loss function L, which depends on the gap between the log probability of y plus and y minus. So DPO just corresponds to one choice of this L, but right now there are many other choices. And the point here is that to minimize this loss function, you need to increase the gap between the log probabilities. Okay, and intuitively, what at least I expect it should happen is the probability of y plus will increase when we minimize the loss, and y minus will decrease. But when you actually run these algorithms in practice, what you often see is that both of them decrease. Okay, this is an illustration of what you often get. This is the log probability of responses as a function of the training steps. And you see that the gap is opening up. Okay, the loss is stably minimizing. The log probability of y plus minus y minus, this increases. But the way that gradient-based optimization often does it is by decreasing both, just at different rates. What this implies is that there exists some other responses, here it's depicted by z, that must increase in probability. And we don't know what these z's are. Okay, they're not in our training set, we're not accounting for them. This may not be problematic. Okay, we can say that this is benign. Maybe this z that increases instead is very similar to y plus. So it doesn't matter to us if the model produces y plus as z and not y plus. But on the face of it, maybe it's catastrophic. Maybe this z can be opposite to what we intended to do. And despite the prevalence of likelihood displacement in practice, it was not clear why it happens and also what are its implications. Can it be catastrophic? In which settings? What can you do with it? And this is the gap that we aim to address. And first, I'd like to show that this can indeed be a problem. Okay, when you try to align the language model and can lead to surprising failures. For example, let's say they want to train our language model to refuse answering unsafe prompts using these direct preference learning methods, for example, DPO. So we can follow the standard vanilla pipeline for doing so. So first we need to collect the preference data. And the way we do that, we take a set of unsafe prompts from some existing benchmark. These prompts can be, please give me instructions on how to build a bomb, and we want the model to refuse to answer. And then we need to collect preferences. So a typical way to do that is you insert the prompt into your language model and sample 2 candidate responses. And then what you need to do is just label these responses to a preferred and dispreferred one, where what we want to do is to consider refusal responses, ones that refuse to answer, as better than non-refusals. And then we have our data set of prompts and pairs of responses, and we train over them. Now, what we want to happen, okay, we start from 2 language models, which are already moderately aligned. The refusal rate is the percentage of unsafe prompts that they refuse to answer. And what we intend to do is we want this to increase. We want them to refuse more unsafe prompts. But what actually happens is that this substantially drops. Okay, when we train the language model using DPO to refuse more, it actually complies with more prompts. Okay, what is going on is that you have likelihood displacement, which shifts probability mass from the preferred refusal responses to other harmful responses, which are not in our training set, that actually answer these responses. Okay, and to me, this was quite remarkable how substantial the drop is. Okay, initially when we run these experiments, we had initial insights theoretically that suggested that this might happen, but it was still quite remarkable to see how significant the drop is. Because we try to align the language model and unintentionally becomes unaligned. Okay, so to try and understand why this happens, we analyze the learning dynamics that these methods induce. Okay, we characterize how does the probabilities of the model, specifically the probability of the preferred response, evolves during gradient-based training. And I'll cut here right to the chase and say that what we show is that examples whose preferences are more similar in terms of their hidden embeddings are the ones that lead to this phenomenon. Okay, and this similarity is in a certain sense that pops up from our theory. We call it the centered hidden embedding similarity score, or in short, the CHESS score. Because this is a score, you give it a prompt and 2 responses, y plus and y minus. And it depends on the hidden embeddings that the language model produces for these responses. So the exact form is not super important. You don't really have to parse this. What you need to know is that it depends on the hidden embeddings, and it is very efficient to compute. You just need a forward pass through your model. The nice thing now is that once you have this similarity score, then we can go back to our experiments, okay? And now maybe you can try to filter out examples with a high score. Okay, only train on examples that have low chess score. And we see that if we do that, if we filter our data to remove preferences which are more similar in this sense, then now we don't have a problem. Okay, now the refusal rate increases as we expect. And this shows that by collecting better data or filtering it, we can avoid these undesirable outcomes. And the similarity score that we give may be useful for that.
Which figure do you use for the event?
It is the final. So you have usually you take your prompt and your response, you enter into, it's a transformer usually, and the final layer before you multiply by the unembedding matrix that gives you the logits. So it's just the final layer hidden embeddings of the response. So just maybe to make it, so not super important, but here for each token, the response, you get a hidden embedding at the final layer of that transformer. So here it's just you sum them up and you take the inner product with the sum of the y minus, and you need to reduce something to, this is why we call it the centered score, just to make sure that if just the hidden embeddings of this have a large norm, it doesn't inflate your score artificially. And this pops up from the theoretical analysis. Okay, so getting better data can mitigate this issue. Another way to try and combat it is change the objective, add some regularizers, modify it. And this is something that also several follow-up papers have done, and you can feel free to check them out.
In the intuition behind this chess.
Yeah, so the intuition. Okay, so I think it'll be best to get it actually from the objective itself. Great. So when will the probability of y plus decrease? Actually, okay, how does the gradient of this objective look like? So we have the derivative of L, which, okay, it's some constant. And then you have the gradient of y plus minus the gradient of y minus, right? Now, for this to decrease, you need the inner product of the gradient of y plus with itself to be lower than y plus of y minus. So actually, the gradient of y minus has a larger inner product with that of y plus than with itself. And then you just open up these gradients, and these gradients depend on the hidden banks. There are some other dependencies which are less critical, but basically the score is due to the dependence of the gradients on the hidden bank. And this is why you have also the inner product between y plus and y minus, and y plus with itself. Okay. So the theory here is quite simple. It's just straightforward looking at the gradient and seeing when will a gradient step lead to a decrease in the probability of y plus. Okay, are there any questions perhaps? Great, so I'll conclude. So what we saw today is two methods for aligning language models. For RLHF, we discussed what makes a good reward model from an optimization perspective and saw that beyond being accurate, we want our reward model to induce sufficient reward variance for allowing for fast optimization. We then use this to discuss how more accurate reward models are not necessarily better, in contrast to how they're currently evaluated, and also discuss the limitations of existing reward model benchmarks in terms of how they are independent usually of the language model that you try to align, and this maybe means that you can't really choose which reward model to use based on such benchmarks. And in terms of practical applications, we saw that the relation between reward variance and optimization can help us design new data selection, policy gradient methods. And I believe that we're just scratching the surface here. There may be many other applications that we can use reward variance for improving policy gradient optimization. For direct preference learning, we talked about how they can suffer from this likelihood displacement issue, where they actually don't increase the probability of preferred responses, and sometimes they send it to somewhere which is problematic. And our theory, which is a theory and experience as well, which I just briefly mentioned today, they suggest that examples with similar preferences in terms of a certain score, the chess score, are the ones that lead to likelihood displacement. And then we saw that by filtering or getting better data, and also by changing the objective, you can try to avoid these issues. Now, going forward, by now we have numerous alignment algorithms. Okay, RLHF and DPO are the main ones, are the most dominant, but now there are numerous variants. Okay, every week or so, you get a new method coming up. And despite the rapid increase in the amount of methods that we can choose from, there's still very limited understanding, even of basic questions. Okay, the loss landscapes, the implicit bias, how this affects generalization. And this limited understanding, as we saw, can lead to undesirable outcomes. And whether this is just inefficient training, okay, maybe we choose a reward which is not good for our policy. Maybe it's even safety concerns. Either way, as these models are getting larger and larger, these sort of mistakes are becoming more costly. And this leads me to believe that in order to make efficient and reliable progress in training and deploying these AI systems, theory may be necessary, or at least it can be extremely useful. Okay, and this can also be mathematical analyses, but also experiments, empirical investigations that give us more principled guidelines. And to finish, I'd like to give a couple of more concrete directions for future work, which at least I find interesting. So the first one relates to policy grain optimization, which we talked about quite a lot today. So in the context of supervised learning, we want to minimize some loss function over labeled data using usually grain-based methods. So in this context, the implicit bias and optimization dynamics of these methods have been extensively studied. Okay, we still don't have a complete understanding, but we do have a relatively good conceptual understanding, at least in some settings. And this was studied also by people in this room, and also some of my prior work. And we do have, I'd say, a decent understanding of what's going on in this setting. However, when we move to reinforcement learning, where we try to maximize the expected reward, it's just a different type of objective using policy grain methods, which is maybe some different heuristics than what people do in supervised learning. And actually, we don't understand that much the optimization dynamics and implicit bias. And this is becoming even more important as these methods are adopted more and more for training language models. For example, nowadays, a lot of the focus is going on training using reinforcement learning for math and reasoning type of tasks. So the algorithm and the results that we show is, here I focus on RLHF, but it applies just as well to these type of settings. And we still don't understand how we can improve optimization there. Okay. And the second direction relates to going beyond reward-based alignment. The methods that I covered today both assume that you have this ground truth reward, which captures to a large extent human preferences. A limitation, though, of reward-based preferences is that they're transitive. Okay, they can only capture transitive preferences. If A has a higher reward than B, okay, it is preferred over B, and B is preferred over C, then necessarily A is preferred over C as well. However, it is known that the preferences of humans are not always transitive. This is something that has been studied actually in the econometrics literature several decades ago. And this leads to the question of how should we relax this restriction and when is it beneficial to do so? One good example, I believe, is recent game theoretic formulations, where instead of maximizing a reward, they formalize alignment as a zero-sum game between two language models that produce responses. And now to align your language model, you need to solve this game. You need to find the minimax winner. This gives us a new solution concept, but we don't know yet when is this better. Okay, when does this lead to more efficient training in terms of the optimization, sample complexity? When is it beneficial to use this approach over reward-based alignment, or maybe even some other approach? Okay, and I believe it's important to better understand this. A more high-level issue, both with reward-based alignment and game theoretic approaches, is that they rely on very limited feedback. Okay, you get only a single scalar or bit, pair of response, or even a pair of responses. And it's going to be important to leverage richer forms, more structured forms of human feedback. Intuitively, we want to get more information for each unit of human effort. Okay, if someone is going over a response or two responses and telling you which one is better, then it's not that much more work to also mark perhaps which part of the responses are good or not, maybe even give some natural language feedback. And this is a challenge both for practice and theory. Okay, how we can design algorithms that use this type of feedback, and how can we formalize when is it beneficial, what benefits they bring, and so on. So this is what I had for today. So thank you for your attention, and to my collaborators in Apple and Princeton.